How's it going, everyone? In this video, I'm going to be discussing aqueous equations. And so up until now, all the chemical reactions that you have seen written out have been in the form that we call molecular equations. And in molecular equations, all of the substances, molecules, ionic compounds, doesn't matter. All of the substances are written out exactly they would be if you were going from the chemical words into the chemical symbols. For example, your potassium hydroxide is written out as KOH. Magnesium nitrate is written out as MgNO32. But one thing you should notice about both of these compounds inside of this molecular equation is they are in aqueous form. And so something that we've discussed in the previous videos, if you see AQ following something like potassium hydroxide or magnesium nitrate, it means that this solid stuff was dropped into, well, in this case, dropped into water. And so, as we've discussed, potassium hydroxide does not exist as potassium hydroxide in water. Once you place solid potassium hydroxide into water, you are going to form potassium ions and hydroxide ions. Very similarly is if you take magnesium nitrate and place it into water, that MgNO32 does not exist anymore. As soon as this stuff hits the water attacks it, starts ripping it apart, and you have magnesium 2 plus ions, and in this case, 2 NO3 minus ions. And so even though they're not written out in the whole entire form, whenever you write the molecular equation, if you want to get a better idea of how these ions move around, or what real ions are present, you have to move on to this next form of equation, and it is called the complete ionic equation. So as I stated, potassium hydroxide, magnesium nitrate, even the potassium nitrate on the other side, if it's written as aqueous, and this term will come up in the next video, and we know it is soluble in water, we know that these guys are going to completely break apart. And so when we write the complete ionic equation, we write it in that form. And so strong electrolytes, which again we kind of talk about a little bit, we will talk about more about here in the next videos or so. But aqueous substances, strong electrolytes, anything that is written as aqueous that we will talk about that 100% of the time will completely break apart, you will write it out as broken apart. And so for example, your 2KOH that we had from the previous slide, same deal here. So your 2KOH will form 2 potassium ions as well as forming 2 hydroxide ions. Remember, KOH, each KOH contains a potassium and a hydroxide. So if you have 2 of them, you need to have 2 of your potassiums and 2 of your hydroxides. Please note, both of these ions should still have aqueous following them because aqueous just means floating around in water. And so same deal with magnesium nitrate, you form a magnesium 2 plus ion and 2 of your nitrate minus ions. And so one of the pitfalls I've seen a few students fall into in the past is whenever you write these things out, write out the complete ionic equations, you cannot forget about your subscripts and you can't forget about your coefficients. And so make sure that you're accounting for all of these ions, polyatomic ions or metallic ions, whichever. You need to make sure that you're accounting for all of the ions that are present on both sides of the chemical reaction. So on this side, 2KNO3 will produce 2K plus ions and 2 of our nitrate ions. And then we have this guy. So magnesium hydroxide. One thing that we'll talk about in the next video or two is hydroxide ions are normally going to create a substance that is insoluble in water, meaning the fact that it is going to maintain its intact structure even if you place it in water. An example of this could be if you take a rock and you place it into a bucket of water, it's not going to just break apart into all its tiny little pieces. It's just going to become a wet rock. And so in that instance, you are not going to have any breaking apart, you don't have any dissociation, you don't have any ions that are being formed. And so something that is solid does not break apart. Insoluble substances, weak electrolytes, and non-electrolytes are written exactly the same form as they would from the molecular equation. In addition to that, solids, liquids, and gases, they are typically not dissolved in water. And so one example that I can kind of give is a soda can. If you have a carbonated soda, as soon as you open that can up, you hear that psst, that is just gas escaping out of the canister. And so you can push gases into water, you can kind of shove them and pressurize them into water, but as soon as they get the chance, they're getting out of there as fast as possible. And so that's why if you have a soda can and you leave it out on your desk for about 2 hours, all that gas is gone. It all has escaped out of the liquid because it didn't want to be there anyways. And so one thing I have to draw your attention to here is something called the complete ionic equation. It should imply that you're looking at ions. And in order to make sure that all of these are ions, you have to remember the charges. And so ions need charges. If you don't include the ions, you are messing with science here, because there's a huge difference between adding 2 potassium ions and 2 magnesium ions than there is adding potassium and magnesium. So remember ionic charges for your ionic equation. And so one thing you can kind of note here is every single one of these atoms is accounted for on both sides. In addition to that, all the charges are going to be accounted for and canceled out. Hopefully should be equal on both sides of your equation. Atoms are balanced, charges are balanced, masses are balanced. We have not violated any laws of science here. And so, another example is if we have a molecular equation talking about silver nitrate being added to sodium chloride to produce sodium nitrate and silver chloride. And so in this case, I just want you to write out the complete ionic equation. So we need to pay attention to what is going to split apart and what, if anything, is going to remain completely intact. Silver nitrate, I tell you it's aqueous, and so again, that's telling you that silver ions and nitrate ions are going to be formed. Your sodium chloride, and if you've watched all my videos up until now, hopefully this one's going to be the trick. Sodium chloride, always going to be table salt, is always going to dissociate into sodium plus ions and chlorine minus ions. Please notice, aqueous, 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 aqueous. As soon as you mix these two solutions of silver nitrate ions and sodium chloride ions, you just have a bunch of ions floating around into your beaker or bucket, whatever you're using. On the other end of this arrow, we have sodium nitrate, still aqueous, and so this is still going to break up to sodium ions and nitrate ions. However, silver chloride is a solid, meaning the fact even if we take this stuff and we put it into water, it's going to stay a solid. And so here you're going to have a solid remain be solid. The molecular formula stays the molecular formula even in the complete ionic equation. And so one additional thing you should notice here is some of these ions don't really change too much. And so getting rid of all these arrows here, starting fresh, we have silver plus sodium plus chlorine minus gives us silver chloride, sodium plus, and nitrate ion. Notice I did kind of switch things up here, but I'll show you why here in a second. And so, some of these ions appear exactly the same. And so if you take a look at silver plus, kind of go over here, there is no silver plus. There's AgCl, but there is no silver plus aqueous. Same kind of situation with this chlorine minus. Chlorine minus here, there is no Cl minus on this other end. And so we know something happened to our silver plus aqueous and our chlorine minus aqueous. But if we take a look at our nitrate ion, I'll be damned, nitrate ion. If we take our sodium plus ion, it looks exactly the same on both sides of those equations. These are what we refer to as spectator ions. And so spectator ions do not partake in the chemical reaction. All they really do is float around. And so in this situation, the only reason why nitrate showed up to the beaker is because it was part of this silver nitrate. The only reason why sodium was even invited into the beaker was because it was already attached to this chlorine. But as soon as you add silver nitrate into the same beaker as sodium chloride, the chloride and this silver ion will join together and actually create silver chloride. They actually do something. The nitrate ion becoming nitrate ion, sodium ion becoming sodium ion, nothing happened. Those ions just entered the solution, they entered the beaker, and that's all they did. After that, they just floated around. And so the next concept here is known as the net ionic equation. So the net ionic equation arises whenever you have your spectator ions canceled out of the overall reaction. And please note, this isn't really necessarily getting rid of these ions. I am not violating a law of science or physics here. I'm not making them disappear. I'm just saying they didn't do anything. And so, in the end result, if you want to know the final thing that actually takes place in this chemical reaction, silver plus and chlorine minus joined together to make a silver chloride bond, and they became a solid. But again, dropping these guys out of the equation, you're not destroying them, you're not completely getting rid of them, you're just saying they showed up and did nothing at all. And so another example is very similar to this. I just wanted to show you another one here. Is if you have something like silver nitrate, aqueous will break up into two silver ions and two nitrate ions. Your sodium carbonate will break up into your sodium ions and your CrO4 ions, two sodium ions. And then same deal on this side, two sodium ions, two nitrate ions, but this Ag2CrO4 is a solid. And so here, this will not break up. This is something that is being formed inside water that water doesn't like, and it kicks out of the system. And so if you look here, your nitrate ion becomes a nitrate ion. Your sodium ion becomes a sodium ion. Nothing happens with these two guys. And so in the end result, nitrate, sodium are both canceled out. This entire sodium nitrate is canceled out. We're looking at two silver ions, our CrO4 or 2 minus ion to create Ag2CrO4 solid. Another example is start completely fresh. And so I want to write the ionic and net ionic equation for the following reaction. And so I have Na2CO3 aqueous. So you have to ask yourself, what is going to be formed, if anything, from this aqueous compound? Because I am specifying, and because you don't know any better yet until the next videos or two, then here you have to understand aqueous means that this is going to form sodium ions and carbonate ions. But pay attention to how many. It's going to form two of your sodium plus and one of your CO3 2 minus. Same deal with the HCl aqueous. In this case, you're going to form two of your hydrogen pluses and two of your Cl minuses. On the other side, we have sodium chloride. Hopefully, I don't have to give any more explanation about that. But it's going to form two sodium ions and two chlorine ions. Please notice, up until now, I have aqueous, 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 aqueous. And last but not least, we have our CO2 gas and our H2O liquid. As I mentioned before, gases, especially CO2, this is the stuff that comes out of your soda can as soon as you open it up. But CO2 does not dissolve in water. It cannot be aqueous. H2O liquid. This brings me to a point that I need to definitely make clear. You cannot have aqueous water. Remember, when you put this AQ after the sodium chloride, you're implying that you took solid sodium chloride and you dumped it into water. If you take water and you add it to water, chances are highly unlikely that that water is going to dissolve in water. And so please note, do not write H2O aqueous. It's just something that you might get in the habit of accidentally doing. Just stop the habit right now. Try to avoid it altogether. So again, hopefully it makes sense. Water doesn't dissolve very well in water, so your H2O liquid will stay exactly as H2O liquid. Solids, liquids, gases will take the exact same molecular formula they had in the molecular equation. And so now if we look at this, just need to go through and see what guys look exactly the same on both sides of that equation. So we have 2 Na plus aqueous on this side. We have 2 Na plus aqueous there. We have a CO3 2 minus aqueous. It doesn't exist on this side, so that guy can remain. 2H plus, nope, no 2H plus. This one can remain. 2Cl minus, 2Cl minus. So in order to go from our complete ionic equation into our net ionic equation, let's get rid of these guys that didn't do anything. And so the end result here, we have the, again, net reaction is going to be CO3 2 minus plus 2H plus to produce our CO2 gas plus H2O liquid. And so when it comes to actually writing these things out and to writing the net ionic equation versus the complete ionic equation, the spectator ions, usually, and I guess here's a heads up, if you have these things already written out for you, anything that appears on the right side of the chemical reaction as aqueous has to be your spectator ions. The whole idea is if it is product as aqueous, it means they're floating around after the chemical reaction has gone to completion, which means they had to have been floating around before the chemical reaction actually occurred. And so, again, if this is written out for you already, if we tell you to aqueous, product side that has aqueous, has a compound as aqueous, that is most likely going to be your spectator ions. Anything that is not aqueous actually took part in the chemical reaction.